This video is for the Edexcel GCSE in Astronomy topic 15, Our Place in the Galaxy. And as is customary, here is a list of the specification. So you can see we're covering a lot of content here today. Feel free to pause and zoom in if you're interested, but let's move on to the content, the interesting stuff. First of all, we're going to look at the appearance of the Milky Way. Now, to us, the Milky Way does not look like this because we are in the Milky Way. So there's no way we could see it from this particular point of view. We are on one of the spiral arms, and we've seen other galaxies with spiral arms, and so we can make certain predictions about what our galaxy would look like if viewed from a great distance away, or if viewed from outside our galaxy, which is what this is an image trying to show. But it is an artist's impression. It actually looks like this to us. A band of stars across the sky, and you can see in this animation, this is a time lapse where the Earth is rotating and the frame has been fixed so that the stars in the sky do not appear to move. So we have that band of stars across the sky, which night after night after night are going to appear to be the same, in the same positions, just because of how long it takes for anything to appear to move from our perspective. Okay, from the Earth, the stars are a very long way away, and although they're all moving, we're not going to see any movement in our lifetime. I wouldn't say they move slowly, it's just their angular movement is very small. So it kind of looks like a milky or cloudy region, like a road of milk, which is what galaxy means. The word galaxy, that's the etymology of it, road of milk. And that's where the word Milky Way, or the name Milky Way, comes from. If you look at the Milky Way from the southern hemisphere, it looks a lot more impressive than from the northern hemisphere, and you can see there are these bands that are dusty. Well, we don't know they're dusty. Well, we do, but you don't know when you're looking at them. They just look like dark bands obscuring the light from behind. I suppose you could think they're an absence of stars, but that would be unusual. Why should there be an absence of stars along those bands? So those bands are where there are clouds of dust blocking the light from behind. But from the southern hemisphere, you can see this central bulge right here, very brightly, and you can see that it's about the same amount on the top and the bottom, so we know we're near the middle of one of the spiral arms somewhere. And if we look out of the plane of the Milky Way, in other words, rather than looking towards this patch of sky, we'll look all the way over here somewhere, way off the picture, then the stellar density is far lower, there are far fewer stars there, so we know the stars are somewhere along a disk with a bulge near the middle. And you compare that to other galaxies that we've seen, and we can make some good predictions. So this is where we think the Sun is in our Milky Way. Again, an artist's impression. And in this particular picture, it's showing that the stars that we can see in the night sky are actually relatively close to us compared to the rest of the Milky Way. Now, obviously, you can see the Milky Way, that lovely band of stars, including that central bulge, on a particularly dark night, so this isn't entirely accurate. You can see right the way through to the bulge. You can't see what's behind it, of course, because the bulge is in the way. But I keep calling it the bulge, perhaps we should call it the galactic nucleus. But anyway, we can't see the other side of it because of the galactic nucleus being in the way, but we can see very bright stars that are near us. And we can also see things with the naked eye that aren't even in our galaxy. So it's not entirely true that all of the stars that we can see in the night sky are close to us, but it is where the majority of them are. So this is an artist's impression of the Milky Way when viewed from above, which of course we can't do. From when viewed from inside, or maybe just sideways onto the Milky Way. This is a very rough diagram. I threw this one together in a hurry. You've got your central bulge here, that's the galactic nucleus. We've got the galactic disk extending out, and we're on that disk somewhere, probably about here-ish. And then we can see globular clusters that aren't within the galactic disk. These are clusters of stars that form into little balls, but they're not part of the Milky Way disk. And you can think of them perhaps as very close satellite galaxies, but they're very small, so probably don't satisfy the requirements for a galaxy. Again, this is a bit of an artist's impression, trying to show what these globular clusters, these cloudy patches of stars that form little balls, would look like around a galaxy. I don't think that's a genuine photograph. So that's what the Milky Way looks like, and that's the basic structure of the Milky Way. Now the spec moves on to parts of the electromagnetic spectrum that are very useful for being able to determine the shape of the Milky Way and getting information from parts of the Milky Way where maybe we can't get information using visible light because there's stuff in the way. And one particular part of the electromagnetic spectrum that's very useful is a very narrow band of wavelengths, in fact, very narrow band of wavelengths, in the radio wave part of the electromagnetic spectrum, the 21 centimetre radio waves. So very narrow band of radio waves. Now, where this electromagnetic radiation comes from is absolutely fascinating. Usually when we think of electromagnetic radiation being emitted by atoms, it's because of de-excitation, which is where electrons reduce their energy level, and the light that is emitted is in packets of energy that are equal to the reduction in energy of the electrons when they reduce energy level. Well, that's fine, but that's not what's happening with these types of radio waves. Now, with these types of radio waves, it's caused by the electron staying in the same energy level, but just switching its spin. And I find this absolutely fascinating. It's probably not something you need for your Edexcel GCSE in astronomy, but come on, it's good stuff. So it turns out that even in the ground states, so we've got very cold hydrogen atoms, they're in the ground state. Even in the ground state, if the spin orientation of the proton and the electron in our hydrogen atom are orientated in the same direction, then that is more energetic than if the spin direction of the two particles in the atom were in the opposite directions. And so flipping the spin of the electron causes a reduction in energy of the atom. Not a huge amount of energy, but that's why we are getting radiation emitted that's of particularly large wavelengths. And this particular wavelength, 21 centimetres, that corresponds to this transition. And we've done this in a lab. We've measured this in the lab. We know this is the transition that's responsible. So if we are detecting 21 centimetre wavelength radio waves, it means that we know there is cold hydrogen that is in that particular part of space where we are detecting this radiation originating. Because if the hydrogen were in a hotter area, so the electrons would be in a higher energy level because of collision between hydrogen atoms causing excitation, then we might get a tiny bit of this radiation emitted, but it's going to be nothing compared to the amount of radiation, the intensity of radiation we get at other wavelengths. So it's going to completely saturate our signal, and it'd be difficult to pick out this stuff. So if we can detect this stuff, 21 centimetre microwave radiation, radios, not microwaves, 21 centimetre wavelength radio waves, not microwaves, then we know there's cold hydrogen in that part of the space. Now, what's special about this type of radiation, because it's got a very long wavelength, it can penetrate deeply through matter. Which means that the stuff in the galaxy, the dust and other things in the galaxy that would absorb certain parts of the electromagnetic spectrum, this radiation can penetrate it pretty well, which means that we can determine where there is cold hydrogen, even if there's other stuff in between us and it. Now, remember what I said about the signal becoming saturated with other radiation, but because the Earth is orbiting, then we're looking at a patch of the sky. We're going to get a small parallax effect, and we should be able to pick out if there is a consistent source of 21 centimetre radio waves coming from that patch of sky behind something else. And now people cleverer than me have looked at huge amounts of data to understand and get to the bottom of how all this stuff works, and figure out where all this radiation is coming from. We can also use this 21 centimeter radiation to investigate things like galactic rotation. So as the galaxy rotates, then it's going to cause a redshift effect. Now, I'm not going to go into detail about how that redshift effect works, because it is, well, a little bit complicated, but there is a redshift effect that's going to be observable for radiation, any radiation in the galaxy, because the galaxy is rotating. Well, we know what the radiation wavelength should be for this stuff, so if we can detect something which is very similar to this but shifted, and from a particular patch of sky where we think it ought to be moving away from us, then those two bits of evidence together, we can calculate how fast it's receding from us, that part of the galaxy. We can do that on all different parts of the galaxy to investigate galactic rotation. So it's very, very clever. Now, the next slide has got a bit of a problem with it. The next slide, in an ideal world, would have this lovely animation. However, the animation was too large. I'll see if I can get it working. Let's pause the video and see if I can get it working. No, the image is just way too large for PowerPoint to handle, so I've gone to the website. This is from Wikipedia. You can look it up yourself if you want to scroll across manually. It's all Creative Commons license, so it's okay for me to use it, just to get an idea of the scale, an appreciation of the scale. Here we've got the Earth and the Moon, we get an idea of the size of those, and if we can zoom out a little bit, then we have centered on the Sun, the inner part of our solar system, Mercury, Venus, Earth, Mars, and some little rocks floating around that. If we zoom out a bit further, you can see the inner circle of our solar system, the inner part there. Then we have the outer part here. So we've got Jupiter, Saturn, Uranus, Neptune. We've also got the other dwarf planets orbiting at more exotic, more eccentric elliptical orbits. And then we look a bit further out, we can have a look at our closest stars. And so we, Sol, I think we've got a different colour just to make us stand out. We're right in the centre. But around us we've got our closest stars mapped out like this. So this isn't to scale, because if the size of the star as it's been drawn was to scale with the distances, this would be an entirely different situation. This isn't to scale at all, and the sizes of the planets weren't to scale before. So there are certain things on this that are just not to scale, but because if we did draw them to scale, it would be a really boring looking picture. If we scroll out a bit further, we've now got the Milky Way, but here, instead of focusing with the Sun in the middle, we put the centre of the Milky Way in the middle. The Sun's all the way down here somewhere. You can zoom in, you can have a look at that yourself. And now the local group, which is the main attraction, it's what we wanted to look at. This is the local group of galaxies. It's not that exciting. We've got the Milky Way, sure, and then we've got Andromeda. Entirely different. Now I'm going to have to sort of squint so I can see what's going on. Milky Way down here, Andromeda up here. We've got a few other little galaxies in here as well. There's a lot going on near the Milky Way. There's not a lot going on near Andromeda. But that's our local group, just those two. And the further out we go, the more we're going to see. So we've got local superclusters, and then we can go all the way out to here with the entire observable universe, which this has been drawn in a cylinder. It's not going to be an observable universe in the shape of a cylinder, so there are some issues with this, but there you go. This is the animation. I wanted it scrolling across slowly. It doesn't really matter. It's all here, and the local group is the bit that we're going to be focusing on next. Let's go back to the presentation. Right, so Milky Way and Andromeda, they're the two big things that we care about in our local group. There is also the Triangulum Galaxy. It's one of those smaller galaxies near Andromeda, and the Magellanic clouds. Those are near us. There's some debate about whether the names of those should be changed. It's a fascinating thing to read about. By all means, look into it and read into it. Should the large and small Magellanic clouds be renamed? But that's beyond the scope of this video. What might interest you is that Andromeda is significantly larger in terms of diameter, larger in terms of number of stars. It is a bigger galaxy. It doesn't look like it in this picture, but it is. In the night sky, if you were to look up and be able to see Andromeda, It's an interesting thing. Because you can't see Andromeda with the naked eye, it's not bright enough because it's so far away, the light's spread out so far from it that not enough light reaches our eyes that we can see it. But we can see it with telescopes, especially if we use long exposure telescopes. But how big would Andromeda look in the sky if we could see it? Well, you know how if you hold your thumb at arm's length, it kind of eclipses the moon. It's about the same angular size as the moon, is the width of your thumb. Andromeda would be about 6 of those across in the night sky. So next time you look towards the patch of sky where Andromeda should be, and just try and visualize, that's how big it would look in the sky if enough light from it reached us. It's a pretty impressive sized galaxy. Right, so now we're going to move on to the Hubble classification system. In the Hubble classification system, we've got elliptical galaxies, we've got spiral galaxies, and we've got spiral barred, or barred spiral galaxies. SB, S, and E, as the names are given. And the more squashed the elliptical galaxy is, the more lenticular it becomes. But I don't think I saw the word lenticular on the specification, but there we go. So a perfectly spherical galaxy, maybe an S0 galaxy. The Milky Way is actually an SBB, a spiral barred galaxy of this type here, and so on. At one time, this was thought to be a diagram showing the evolution of galaxies over time. We now don't think that is the case at all. So spiral galaxies don't have that bar through the middle. Barred spiral galaxies do, but where do you draw the line? SA looks like it might kind of have a bar. SBC kind of looks like it doesn't. You know, where do you draw the line? It's just a way of categorizing, classifying different galaxy shapes. There's one, of course, that's not included on this list. That is the irregular galaxy. Here's an example of an irregular galaxy. It doesn't really have any shape that fits on this. Now, there's some reasons why you can get irregular galaxies. They could have just formed this way, or they could be the result of collisions between other galaxies, galactic collisions, leaving behind the remnants which have no particular shape. Now, over time, they might, well, they probably will, over time, due to gravity, condense down into a more spherical sort of shape, but at the moment, there's certainly no regular shape to them. This is an example of it here. Now, in the centre of most galaxies, not all galaxies, but in the centre of most galaxies, we have what's called an active galactic nucleus, or an AGN. And if you look towards this blob here, you might think that's a star. It's not a star, it's a galaxy. And you can actually see a wisp of, well, what is that? That's matter coming out as a ribbon coming out from one part of it. And these active galactic nuclei, we believe, have black holes, supermassive black holes, in the centre. And the particles that are trapped in a very close orbit around those supermassive black holes are colliding with each other. That's causing fusion in that region. It's also just causing all sorts of other nuclear reactions, huge amounts of radiation being produced and emitted in all directions. And because you've got a very hot plasma then orbiting very close to the black hole, you've got a hot plasma orbiting, that's going to have its own magnetic field, so you're going to get the plasma that might be ejected coming off as a ribbon in the same way as you get when you look at the sun and you look at a coronal mass ejection from the sun, and we covered that in a previous video, although this is on a much grander scale. So that's an active galactic nucleus. And we know that there's something exciting about them because the radiation we get from them is much too energetic to have come from any stars. So we needed a whole new way of categorizing these things. Let's move on. So this is a type of active galaxy. There's a few of them. The Seyfert galaxies. In the middle of this is an active galactic nucleus. The colouring of this has been modified slightly. It's I wouldn't say it's an artist impression. It is a photograph, but the colouring has been modified to make it more useful for doing real science. These things, very bright, And of all the galaxies we've seen, about 10% of them are of this type of active galactic nucleus. We can see the galaxy around them. That's the key thing about Seyfert galaxies. Whereas quasars, standing for quasi-stellar objects, stellar means star. They just kind of look like single stars. Kinda, quasi, not quite. So they've got similar appearance to stars, but not quite. And they're way too bright to be stars. What we think these are actually nuclei of galaxies where you can't see the stars orbiting them. So all you can see here is the active galactic nucleus itself. These have huge masses, millions to tens of billions of times the mass of our sun. We can see radiation coming from the region around the active galactic nucleus, but it's not stars, they're just gases. And I say just gases, these are excited gases because of how close they are to a black hole. One thing I'm going to point out is you can see there's a bit of a ribbon of radiation, particles, let's say, coming off this quasar here. Here's an artist impression of a quasar where you can see that jet of matter coming out of here, so perpendicular to the plane of rotation of the quasar. And there are some cases where that jet is directed right towards us, and so as this thing might move around, wiggle around, we can see the jet of particles coming right through our right across where our planet is. Wiggle around, I meant, of course, precess. So as the sort of galaxy does all this, or the active galactic nucleus precesses like this, if that jet of particles, that jet of radiation comes right towards us, then we see a sudden brightening of that radiation, and it has a regular period to it. Those have a special name. They're called blazars. It's quite a recent name for these things. And we think that at the centres of elliptical galaxies, just because of how much radiation is coming out, they're probably going to be such a huge amount of mass, it's going to pull it into an ellipse. But it's really hard to tell because all our sensors are saturated by the signal coming from the jet that's just directed right close towards us. It's got a relativistic jet because the particles are so energetic they're moving close to the speed of light. So here is the emission spectrum for active galactic nuclei, or spectra, because there's a different spectrum for each active galactic nucleus. We've got normal galaxies, that's not active galactic nucleus type of galaxies, and you can see the radiation we get from that, a little bit of X-rays, but not much else. And then we go down the list. Radio galaxies emit everything right the way down to radio waves. You've got your blazars there emitting pretty much everything, but interestingly not far infrared. Far infrared is the radiation that's emitted from, actually from pretty cold things. Anything above 0 Kelvin is going to emit far infrared radiation all the way up to very, very high temperatures, but by then we're getting visible light around a few thousand Kelvin, even X-rays at even higher temperatures. You've got your quasars there, which look very similar to blazars. So it's interesting with blazars we're not detecting that far infrared, probably just because of how saturated the signal is from all the other more high energy radiation that we're getting. And you've got your Seyfert galaxies in there as well. So that's galaxies. The question then goes on. Well, the question should get asked, why are there clusters? And then why are there superclusters? Well, the answer is gravity. Gravity pulls galaxies together. It pulls galaxies into their shape, but it also pulls galaxies towards other galaxies. Now, because of the huge distances we're talking about, any motion takes a very long time to happen. But the universe has been around for a very long time, so it's had plenty of time for it to happen. So there are two theories for how galaxies form and how clusters and superclusters of galaxies form, and we'll go to that in a second. But what we have noticed is that if you look at the cosmic microwave background radiation, where it is brightest, most intense, so in this diagram where it's red, where you get most of this microwave radiation, which is radiation that's been stretched out, red-shifted, but right from the beginning of the universe, right from when the universe first became transparent, that's the radiation that was emitted, and over the billions of years it's been travelling, it's been red-shifted, so wavelengths have been stretched out, now they're in the microwave region. Those red regions down here, you tend to find galaxies are more densely packed in those sorts of areas, and these cooler regions where there's less cosmic microwave background radiation, you actually have lower galaxy density. That's interesting. And we don't think it's just where there's more galaxies, there's more of this radiation, because this radiation originates from before the galaxies could have formed. And if you think, well, the galaxy is possibly interfering with this radiation, well then why wouldn't you have less of the radiation where there are more of the galaxies? It actually doesn't work that way. It's the other way around. So trying to get our head around why you've got clusters, this is something to bear in mind. When the universe first formed, it was not uniform. So let's move on to the next slide. The two theories. The first theory is that the matter right near the beginning was gravitationally attracted in some areas. It was attracted more closely than others, and so you ended up with the galaxies forming. Seems reasonable. Attraction stronger in regions with higher density, matter clumped together, and eventually those clouds were dense enough to form stars, and eventually those stars, there's enough of them nearby, so they're all clumped together and they form galaxies. So this is a sort of top-down approach. However, if that was true, how would you still get stars far away from galaxies? And they do exist, and how would that happen? Because surely in the time that the universe has been around, if it was all mostly dark matter, all sort of spread out, and then where it's slightly higher attraction, all that matter comes together until eventually it's dense enough to form stars, and those stars are going to be close enough together because of how clouds collapse, then how would you get stars so far away from everything else? Why wouldn't they have been swept along with all the other matter that was condensing down to form the stars? I've got a little animation thing here which may or may not work. There we are, it is working. Galaxy evolution. I don't think there's sound on this. I hope there's not sound on this, otherwise you won't be able to hear me as I'm talking. It's supposed to show the idea of top-down. Initially, there weren't any stars, it was dark, and then the stars started forming as the matter got dense enough, and the galaxies formed just because the stars were dense enough to pull towards each other. So that's what we mean by a top-down model, a top-down theory. Thank you, NASA. Everything NASA makes is in the public domain. So, you've got low dense clouds, and then over time you get stars forming. Now you can see those points are getting brighter and brighter, and then they're condensing towards each other. And we won't watch it for a second time. We've seen it once. Once is enough. So what about the bottom-up theory? Well, the bottom-up theory is the idea that the stars formed first, and then they all clumped together. So, top-down, you've got matter clumping together, and then you've got stars forming where it gets dense enough. But by then, the matter's clumped together enough to basically be where the galaxies would end up anyway. The bottom-up, it's the other way round. The matter condenses enough to form the stars, and then it's the stars that are attracting to each other. They're slightly different, ever so slightly different theories. It's difficult to pick out the difference between them some ways, but there we go. So the problem with this bottom-up theory is that you can't make it predict the rotational speeds of the galaxies properly, or the sizes of the galaxies properly. So it actually looks a bit more like it's a mixture of two of these models. There's the top-down model forming galaxies, but there are bits where it is less dense, where the bottom-up theory, where stars are forming first, can also happen. I mean, why not? Why not both of these models happening at the same time? There's no reason why not. They're very similar anyway. It's just about matter distribution, whether it's going to clump together on a big scale first and then you make stars, or clump together on a small scale first and then clump together to make the galaxies. Which way around does it go? And that is the end of this video. Nice short one. Hopefully that has been useful. Hopefully you're going to be able to use that as part of your study, as part of your revision. One more video to go. The last video about cosmology. Thank you very much.